Let's do a brief treatment of probability. What we're going to do in this is we are going to look at basic premises of probability, and then we will use those as we go forward in our statistics class. So what happens, and what we've been looking at rare events. And rare events or unusual events tell us that the statement that we have assumed is true, or someone has assumed is true, is probably not true because it wouldn't happen simply by accident. And so in statistics, what we do is we look for evidence against statements, because you can show that something's probably false, but you cannot prove that it's true. So this is why some of the statements that you've run across in the course already seem like we're going backwards. So we cannot show that anything is ever true, but we can gather evidence against the statement. And when you find strong evidence against a statement, you can show that it's probably false. So that's what we use in statistics. We use probability to either show there's no evidence against a true statement, so it's probably true, or there is strong evidence against a true statement, so it's probably false. So what we're going to do is we're going to talk about the probability of an event, and there are going to be just some very simple equations here, nothing that you need to really memorize because they're pretty intuitive. Now, the most important thing is how to interpret those probability values. Now we need some definitions. An event is any outcome of a procedure that you're interested in. A simple event can't be broken down any further. And the sample space is all the possible simple events. Now on the next slide I have an example to show those. So here we go. Our procedure is a family that has one baby. The event that we're interested in is going to be one girl, but the sample space could have either been a boy or a girl. If we're looking at a family with 3 children, 3 births, we want to know about the event of 2 boys and a girl. Well, that can happen when order counts as boy, boy, girl, boy, and girl, boy. So this event is made up of 3 simple events. And our sample space is looking at 3 births in order how they could happen. These first 4 would happen looking if the first one's a boy, and the last 4 happen if the first birth's a girl. And so there are 8 possibilities in the sample space, 3 simple events in the event we're interested in. Now, what probability is, it's a science of chance behavior. And the thing is that it's unpredictable in the short run, but in the long run, it's very regular and predictable. Now, this is what happens when you go into a casino. And this is one of the reasons why people find gambling entertaining. Because in the short run, it is very difficult and almost impossible to predict the outcome of any single play of any single game. But in the long run, over a long pattern, it is predictable. And the casino can, using this, can say that I know over 1,000 plays of blackjack that the house will win this many times. And that's the reason why the casinos are in business, because the house will win more often than the player wins. And because the house wins more often, they know they will make a profit, so they will be able to uh, build the building, cover the operation costs, etc. If over the long run the casino would not win more often, they'd go out of business. And so we are going to look at random samples and look at randomized comparative experiments. Now, we know that individual outcomes are uncertain, but over many, many repetitions, we do get a regular distribution. And we look at the relative frequency or the proportion of occurrences, and they actually settle down to one value over the long run, and that is the probability of that outcome. Now, these probabilities can be determined or checked by a long series of independent trials. When you do the trials and you count them, this is called empirical data. It simply means that it was observable. So it's experience with many samples, and sometimes we do this with simulations, computers, random number tables, and we'll talk about this more as it becomes applicable in future chapters. Now, notation. A capital P denotes probability. The capital letters from the beginning of the alphabet denote specific events. And when you see P outside the parentheses and another letter inside the parentheses, that's read as the probability of A. Now, how do we compute this? Well, we can use relative frequency approximation. And what this means is we're going to look at the number of times that the event we're interested in happens out of the number of times the procedure was repeated. So if we go back to the boys and girls, we can do this, but we didn't actually observe it. We did it theoretically. That brings us to rule number 2, where we looked at the number of ways that two boys and a girl can occur, and we looked at the number of total simple events that would be in the sample space. And so again, there was 3 ways, 1, 2, 3 ways we could get two boys and a girl out of the 8 ways. So the probability of two boys and a girl out of 3 births is 3/8, 3 over 8. Now, one of the most common relative frequency probabilities that we're all familiar with is flipping coins. And as we increase the number of tosses, that probability does start to settle around 50% of the time. So the dotted black line and the red line are 2 different series of coin tosses. Notice that when we are under 100 coin tosses, that line is all over the place. But as our number of coin tosses increases to 5,000, it settles down to half the time you get heads and half the time you get tails. And this brings us to the law of large numbers. The law of large numbers tells us that as a procedure is repeated over and over and over and over, the relative frequency of probabilities in an event tends to approach the actual probability. Again, let's review some probability models. Remember, S stands for the sample space, which is all possible simple outcomes, simple events. The event is what you're interested in happening, so it's one outcome or a set of outcomes, and it's a subset of the sample space. Then that brings us to the probability model, and the probability model is a mathematical description of the regularity of the way we can assign probabilities to the events in the sample space. Now here's the example of probability for rolling a pair of fair dice. Now, FYI, each one of the 6-sided cubes is called a die, and the dots on the faces of the die are called pips. And so you can see that we have 36 possible ways for a pair of fair dice to come up, and we need to note that a 3 and a 1 is different than a 1 and a 3. So when you're doing your sample space, order matters. Usually when we're looking at an event, it doesn't. So we might look at the event of rolling doubles. So let's look at rolling doubles. Well, double ones, double twos, double threes, double fours, double fives, double sixes. So there's 6 ways to roll doubles out of 36 possible outcomes. So 1/6 of the time is the probability of rolling doubles with a pair of fair dice. Probability rule number 1. And you're going to see these a couple times in a couple different ways. Any probability is a number between 0 and 1. When we're thinking about probability, it's the proportion of times that it's going to occur. If it always happens, it will occur 100% of the time, which as a decimal is 1. Something cannot happen more than all the time. If the event will never occur, it has a probability of 0. If it has a probability of 0, it isn't going to happen. Think of it. The probability that the sun will rise in the west is going to be 0 because it isn't going to happen. The probability that the sun will rise in the east is going to be 100% because it will happen. And this is empirical in the fact that it's observations over the hundreds of thousands of years of history of humanity. So again, possible values for probability range from 0, it isn't going to happen, to 1, that it is. So we either talk about it as a decimal number or as a percent. So it's always going to happen as 100%. It's going to happen half the time will be 50%. It's not going to happen is 0%. Probability rule number 2 says that all possible outcomes together must have a probability of 1. Something is going to happen. So when I toss a coin, what are the possible outcomes? Heads or tails? Now, if it's a fair coin, heads will happen half the time, tails will happen half the time. Now, sometimes coins and die can be created that aren't fair, but still the possibility of all the possible outcomes will add up to 1. So we call these coherent models. When the resulting model, when the total probabilities is not 1, it's incoherent, meaning it doesn't make sense. Probability rule number 3 says that when things can't happen at the same time, if one or the other happens, it's the sum of their individual probabilities. So if we want to look at the probability, or yes, what is the probability of the age of a woman at first birth? So we gather the data and we find that new mothers, 25% of all new mothers are under 20. 33% of all new mothers are between 20 and 24. What's the probability that the first time a woman has a baby, she's more than 25? Well, let's look at this. This is kind of a combination of rule number 3 and rule number 2. We know that the probability that the mother is 24 or younger is 58%. This is rule number 3. But to answer our question, we need to go back to rule number 2. 100% minus 58% is going to be 42%. And then probability rule number 4 is a really good rule, and it really comes in handy because what it says is the probability that an event does not occur is 1 minus the probability that the event does occur. Now, I don't like these examples because they are just, you're guessing at, especially this first one, you're guessing at the probabilities. But if you think it's 80% probability that the defendant is guilty, then you must also believe that the probability that the defendant is not guilty is 20%. This one is better. If you research that the flight you're interested in is at least on time, early or on time is 70%, then the probability that it'll be late is 30% because it can't be earlier on time versus late. There's no other options. So what we do is we put a line over the event that we're interested in to show that it's the complement. And I like to think of complements as A and not A. So the probability that A will occur is equal to 1 minus the probability that not A will occur. That verbiage can be confusing. The probability that A will occur is 1 minus the probability that A will not occur. Sometimes the complement is written as the letter with a prime behind it. So again, this is written, the probability that A will occur is equal to 1 minus the probability that A will not occur. Or the probability of A is equal to 1 minus the probability of not A. And here is a slide that summarizes those rules. Now just relax. There will never be any kind of question that says state probability rule number 3. State probability rule number 4. Just think about them because they really do make sense. They're logical. Now let's look at this, and we want to use our probability rules, and we want to find the probability of rolling a 5 with a pair of fair dice. So how many ways can we make a 5 with a pair of fair dice? Well, we can get a 1 and a 4. We can get a 3 and a 2. We can get a 2 and a 3. We can get a 4 and a 1. If I remind you of the previous slide, how do we get 2 and a 3? Well, there's one way. That's 1/36. Sorry, a 3 and a 2, a 2 and a 3, a 4 and a 1, and a 1 and a 4. So what we're going to do is 1/36 is our probability for each of those events. So the probability of, these are simple events, and rolling a 5 is our event. So our event of rolling a 5 is going to be the sum of the probabilities of the 4 simple events that make it up. So 1/36 plus 1/36 plus 1/36 plus 1/36 is 4/36, which simplifies to 1/9, which we can write as a decimal as 0.111. Now when we write these, we are going to, as a decimal, we're going to write our decimals with 3 significant digits, and we'll talk about that in a minute. So what we're going to do when we round off probabilities, we're either going to give the exact fraction or a decimal if it comes out to be a terminating decimal. But 2/3, 5/9, that's going to come out to be a repeating decimal. When that happens, round it to 3 significant digits. That means that after the first non-zero digit, you're going to go 2 more decimal places. So you have 1, 2, 3 significant digits. Sometimes you might get a decimal that does come out even, but I mean, a fraction that is just difficult to understand because you can't wrap your brain around it. Then change it to a decimal, round it to three significant figures. Now, sometimes we have countable number of outcomes, and what that happens is we can actually assign the probabilities. And when we did our M&Ms project, that's what happened. And we're going to look at that when we do our activities. So we have a countable number of outcomes, and we're going to assign a probability for each individual outcome, and then they have to be a fraction, and the entire probability model, all the probabilities have to add to 1. So here's an example of some probability models. So this is the probability model of one die and what's going to happen when we roll it. Well, in this one, they told us that 1/7 of the time we'll get a 1 or a 2 or a 3 or a 4 or a 5 or a 6. But let's look at the sum there. That's only going to come out to be 6/7. It doesn't add up to 1. So this is an incoherent model. Now let's look at model number 2. Remember that 1/3 is 2/6. So we have 2/6, 3/6, 4/6. Oops, a 4 is not going to happen. 5/6, 6/6. Well, guess what? That adds up to 1. So this is a coherent model. Now, this model also tells me this is not a fair die because the face with the 4 has been weighted in some way, so that is always going to be down. Since the 4 isn't going to happen, we know the 1 is on the opposite side because that's going to happen twice as much as we would expect with a fair die. So that's how they load a die. Just like if you have jelly toast in the morning and you drop it, the jelly is going to hit the floor because it's more dense than that plain bread side. Let's look at model number 3. And again, 1/3 is 2/6, 3/6, 4/6, 5/6, 6/6, 7/6. Oh my gosh, this is more than 1. So again, this is an incoherent model. And model number 4, we don't even have to add it up because our probabilities are not between 0 and 1, and they will not add up to 1. So we know that's incoherent. Model 2 was the only coherent or valid probability model on this page. Now, sometimes we have a compound event, and so it combines two or more simple events. So we're going to talk about the probability of A or B. So that means A is going to happen or B is going to happen, or they can both happen. So we need to find a way that no outcome is counted more than once. So what's going to happen is we find the probability of A, we find the probability of B, but we have to subtract the probability that both A and B will happen, because what that means is we're counting them twice. So again, intuitively we're going to add them in a way that every outcome is counted only once. So for instance, the probability that I get a queen or I get a club is going to be the probability that I get a queen, which is for 50 seconds. Or the probability that I get a club, I did this wrong. There are 13 clubs in a deck of cards. So, and then I have to subtract 1/52nd for the queen of clubs, which this is going to be 16/52. We'll make that look like a 6. And so the probability of drawing a queen or a club is going to be 16/52. Now, if we go back to what I had written and just look at the first part, and we just look at the 4/52, so that's the way to get the queens. And then after we take the queen of clubs out, there's only 12 ways, 12 other clubs, and so that's going to add to 16/52. So what I wrote on the slide is the mathematical rule, and what we did here in talking, that's the intuitive rule. You get to the same thing both ways. Now, that tells us joint or disjoint. Disjoint just means it's mutually exclusive. So when we talked about drawing a queen or drawing a club, those are not disjoint because I could get the queen of clubs. But if I'm going to look at what's going to happen when I toss a coin and when I draw a card, they have no outcomes in common, so they will be disjoint. They are totally separate, where if there's an outcome in common, then you have to only count that piece they have in common just once. When we talk about complementary events, A and not A must be disjoint because it's impossible for an event to happen and not happen at the same time. So A and not A will be disjoint. And again, here are the rules for our complementary events. They're very similar to the rules we had before. So let's look at the rule of complementary events. The probability that A will happen plus the probability that A won't happen, it will be 1. The probability of not A is 1 minus the probability of A. The probability of A is 1 minus the probability of not A. It is as simple as that, and we can visualize it by this. If the probability of A is our circle, then the probability of not A is going to be outside the circle. And that's all there is to it. Now, what I'm going to do is we're going to look at the active learning questions in class, and we'll go over them so you have a chance to look at this, and then we will go over this in class.